Hey, you are in for a treat today. Shh. Trust me. Hey everybody, welcome to the Fireside. My name is Jake. So excited to have you here with me today for this awesome episode with Aaron Williams of Tattcom. If you liked our episodes, our science and physics series with S8, or our kind of machine technology series with Carson Hill of Numa Tattoo, you're really gonna love this one. It's right up the same alley as both of those. We get into some really interesting kind of tattoo geeky types of things. Aaron has slow motion phantom cameras, so we get to like test out needle penetration in skin, ink deposits, all that kind of stuff like that. And really an exciting episode. This is actually the reason that we did this episode was to just kind of get to know each other a little bit and explore some different ideas in preparation for Aaron to come up here to Memphis and us do kind of a long thoughtful deep dive on several different topics when it comes to machine technology and tattoo science and physics. So we'll look forward to that in the future, some of the stuff we do here in person. Make sure you're signed up for our notifications, our mailing list, so that you can be up to date on when that is actually going to happen. We may actually even do it live here in Memphis, so do it more as a workshop where we explore some of these ideas and put all of Aaron's cool little electronic tools to use. So make sure you're signed up for the Fireside newsletter. What else? I think that's it. Let's get into the episode. Hope you guys enjoy it.
So, so why don't we just start with that? Because you're not a tattooer, right? What's your relationship with tattooing outside of Tattcom, like before?
So I've been getting tattooed for since about 2008, and spent a lot of time in tattoo shops. Became friends with several tattoo artists that were doing my work. Would just hang out with them, after my job as a machinist. Solved a lot of problems, tinkering around with things they needed made, little parts here and there, fixed a lot of armrests, other things like that.
Yeah, that's cool. So you were, by trade, you're a machinist?
I was a machinist, yeah, for 10 years. Did CNC machining, and from job shop to custom motorcycle parts. I used to make the big 32-inch wheels and all the stuff for the Harley baggers, the custom parts. And then I transitioned into a shop that did fire apparatus. So that we made the swivels for the bottom of the fire truck ladders and the telescoping extensions that carried the water. Pretty cool job, machining hydraulic and water and electrical swivels. That was pretty intense. So then I went into another shop that was a job shop, and we did aerospace and a whole bunch of external work. We didn't make any products like the other places I worked at, but we took other people's work on, and ISO certified, so everything was inspected and held in tolerances, and taught me a lot about standards and ways to apply that into our industry. So obviously before any of that really got into it, I witnessed the transition from coils into rotaries.
Just at the shop, hanging out at the shop, getting tattooed. The people who were tattooing you were making that transition.
Exactly. Yeah. So I remember coming in, and all of a sudden I'm getting tattooed with rotaries, and just piqued my interest as a machinist, as an engineer. I've always been a tinkerer and making mechanical, electrical devices. So I just picked up I'm a sponge, man. So I just sat around and just soaked it all up throughout the years, and it was I never really knew what I wanted to do. I knew I wanted to do something, but there was always kind of this, I've got all these skills that are collecting, and what do I do with them? And where can I dump this passion? So that's where it was like, finally I found something that's like, I like the art. There's problems that could be solved because I saw some of the equipment coming out, and I just started to pay attention to it and hear how the artists were talking about it. I'd ask them questions about the why behind it, and they just refer to the marketing, which to me didn't make sense. So that's when I started to really, do some digging and look into ways that things could possibly be improved.
Yeah. So did you come into it focused on rotaries, did you have much? Did you ever tear apart coil machines or play with coil machines, or were they part of your experimentation when you started to play around with power supplies?
Had experience with the coil machines, and we actually, when we got started, we were designing a machine that had a new drive system. It wasn't a coil, it wasn't a rotary, but basically it came to a point where just physics took over, and we found out we were chasing down a hole that the numbers didn't line up on this thing, and no matter what we did, we weren't going to solve some of the problems that it inherently had. So it's one of those things like fundamental problems in physics, where no matter how much power you throw at something, you're not going to be able to overcome this law that can't be broken. So
it wasn't the issue was a physics issue, not a cost to construct kind of issue or anything like that. It was just you were hitting a ceiling that you couldn't get through.
Exactly. So the performance just wasn't the design criteria that we had set. The actual prototypes weren't living up to the performance. So we had spent at that point about 2 years, and we hadn't had a company name. We didn't really have anything. So it's just my business partner. My business partner's a 25-year friend of mine. And, we've been, since we were young, man, since we were in school, just always building stuff. His dad was an electrical engineer, so he had oscilloscopes and all the lab equipment in his basement. And then we had like a little machine shop in our garage. So between the two of us living across the street, we're building some crazy stuff, man.
Yeah. So he had more of the electronics background than you, or you guys kind of came up in it together?
We have so much overlap in what we do that it's kind of like, if I were to have a clone, it would probably be, like we're two different people. He doesn't have tattoos, and he's people look at him sometimes and they're like, man, that guy looks boring. But then, when they get to know him, they're like, man, he's a cool dude, because at the end of the day, he's just got a, man, I'm a nerd. So like at the end of the day, like I get really excited over like the tech stuff, over that, for me to go out and get excited about things that normal people get excited about, sometimes it's like, not always easy in that regard, to relate. And, that's where I'm trying to bridge this gap of, I feel like the industry needs the engineering. There's obviously transitions being made right now into more advanced products that have circuit boards inside them. Since day one, power supplies have had some sort of circuit in them that somebody's had to design. So it's either been copies of things that have worked, like how the coil transitioned from a doorbell and nobody engineered a tool from the get-go. Edison had the rotary, and, the coil transitioned in there. But since then, the two fundamental principles of that, I guess there hasn't been much progress into, like, if you look into other areas of technology, of science fiction and things like that, of people that are dreaming and thinking of, like, what is it going to be in 20 years? And how do we start making steps to get there?
Yeah. I've heard some discussions along those lines about just significant leaps in technology overall, just sort of stalling over basically since the kind of the information age, when you think that they would really take off. A lot of the things that we're most proud of are like newer versions of the same phone. People give the example of like the iPhone. It's like, well, how much better is the iPhone than it was in 2006 when it first came out? It's like we went from making these like quantum jumps in technologies to these kind of 10% incremental, inching forward. It seems like across the board.
On the surface, I guess you could say that, but when you look at it as a whole, if you pick up an old device from 10 years ago and you look at where a phone was and you try to do the same things that you do today with your phone, it's leaps and bounds, and a lot of it isn't just the hardware, which is what a lot of people start to look at when they think about the phone. It's the progress in the software as well. So, by supporting the hardware, you're supporting that ecosystem that allows that software to evolve to a point where, you have all these features that now your phone, if you're in a car accident, can call 911 for you, and it can detect that and potentially save your life, where, that's cool uses of technology. There's some bad uses of technology, but there's a lot of good uses of it too.
Sure. What caused so you reach a point with the machine design that you realize that it's not going to work, and then your transition to power supplies from there was just a natural one because of that?
The transition to the power supply was, we'd spent 2 years and a lot of money and a lot of time. This was for me and my business partner, we had day jobs at the time. So we'd get home from our day jobs and we'd work whatever we could on that alone, and then collaborate on the weekends. So Saturday and Sunday and Friday night after work, it would be meet up. And I had at my place office set up that he would come and crash in my spare room, and basically, we would just grind through the weekend and get as much time in, because ultimately that's what matters most, when you're doing something like this. So we've tried to think about how we could use that and where the main benefits of the machine we were designing and what it was going to do, and how we could design something that might be able to bring those to an existing machine. So that's where we came up with the power supply, and saying that a rotary machine, unless if it was a brushless motor, doesn't have a constant speed. And that's something that a well-tuned coil, is going to hold that constant speed. And that's presumably why people like them so much. So why don't we take that and make a power supply that does that on every machine? And not only that, takes it from not having a voltage as a reference, but giving them a tool to accurately determine the speed of any machine. So that way, no matter what they pick up, they know what speed they're running, they can dial in, and they can do their work. So that's where the pursuit of designing the power supply in 3 years of design. And it sounded like a easy transition, but like anything, it was we got out to work with the first handful of machines, and then we went out and tested some more, and it was always more curveballs getting thrown. So
because of the differences in the motors themselves in the machines, or what or just the mechanisms that are different from rotary to rotary, the kind of dampening mechanisms and all those types of things, or what?
It's mainly just the design of what you have to do to be able to, there's no feedback on a tattoo machine to know how fast it's going. So we have to determine this through what's available. And that's pretty much the clip cord or the RCA cord. There's several ways of doing this that are not secret, but to make a universal solution that works across the board is it's not so hard to do it with one machine, but to make something that plugs into anything and then has accuracy within 1% to 2% of error that's a very difficult task. So
yeah. Can you, just to back up for a second, can you give any kind of brief explanation in layman's terms of why a rotary motor, you said unless it's brushless, does not have a consistent speed? Why is that the case?
Yep, because a brushless motor already has a speed controller on it. So a brushless motor is going to have some sort of speed controller. Most of them have an onboard speed controller. So, a brushless motor is a 3-phase motor. Most of them, they have 3 coils in them that need to be energized in a certain sequence to, rotate the motor. Unless if you design a system that reads the feedback from the motor, whether it's through the back EMF or whether it's through a Hall effect sensor, you most of the time just the manufacturers have this encapsulated in the back of the motor. You put a positive, negative voltage to it of a certain voltage, and the controller, that's going to translate to a fixed speed. So as long as you have enough current behind the voltage that you're putting, or the power that you're putting into the machine there, that machine will maintain that speed. The controller in there is going to regulate that speed for you. On a brush motor, that's not the case. The brush motor, you're running a fixed voltage, and basically as the torque load on the motor is varying, it's going to require more or less current. And at that voltage, you're not going to be able to supply that. this is something I've been struggling with because it's such a tough topic to explain that covers like, and this is one of the things that I'm hopeful with you that we can figure out through coming up there and spending some time together and how to break down these things, because you kind of have to understand a little bit of how a DC motor works. You have to understand a little bit about Ohm's law and volts and amps and watts and what power is and what the difference between them is, and really start to understand that, to understand why a brushed DC motor can't hold a constant speed at a constant voltage.
Yeah, that'll be a lot of fun to dive into, and it's one of those things. We had on the Tattoo Weekly this last Monday, Guy Aitchison was on, and he was tattooing Lauren, and we talked a little bit about you. We were doing this. We were originally planning to do this interview that day. That's what the discussion was, and Guy made the statement that that for him, it's intuitive. The feel, he doesn't feel the need to look at a voltage. Like, he's using a Cheyenne pen that doesn't have a voltage readout or anything like that. It's a built-in battery, and you turn it, tilt it, and it changes however. But your point is different than that. It's that regardless of whether you find the proper speed, the proper voltage to work out to make a mark in the skin that works with your hand speed, if the rotation of the motor itself is inconsistent in each stroke, is that, am I on the right track?
What you get down to, or what I've learned, is that what artists are calling bog on a rotary machine. Right now, I've heard different people relate to different things, and the terminology gets so mixed up that it makes my head spin sometimes. But all right, so bog basically I would define as the speed of the machine slowing down, the reciprocation rate of the needle, the hertz, the cycles per second. The machine is slowing down.
Because
when
of the
that happens,
that it's meeting.
Because
right.
There's a load coming on it. Yeah, resistance, right. Load, torque. That that resistance of the skin is transmitted through the needle bar up to the cam or the mechanism that's driving it, and that in turn is torque demand on the motor. So, screen. So like, you have what's called the speed and torque curve of a DC motor. And it's basically saying that at zero speed, and stall torque, at zero speed, the motor's stalled. It's not turning. It's going to require the most amount of current. And then you're going to go up to full speed. The amount of torque is going to drop off. And sorry, I'm trying to read this. The rotational speed's dropping off. Torque and rotational speed. But basically, a motor, as when you start it at zero speed, it's governed by the resistance of the coil. So the only thing limiting current to flowing into the motor is the resistance of the coil itself in the motor. Once the motor starts spinning, it actually starts acting as a generator. So it goes from acting as a resistor of just being the resistance of the coil to acting as a generator. Now it's producing what's called back EMF, or back electromotive force, and it's actually pushing voltage back against the voltage you're trying to push into it. Right? Okay. Now, once these two voltages are equal, the motor can't go any faster. Okay. That's going to be the point where that's the maximum speed of the motor. You can continue to increase the voltage to the motor. It's not going to go any faster. It's going to draw more power, but it won't go any faster. So
will it just produce heat at that point?
Pretty much, yeah, pretty much. So these are inverse relationship, proportional, and this is the stuff that, again, we'll go into, and let me pop over. But yeah, we'll get into that when I come up there and hopefully shoot this content.
Yeah, that's interesting. Just to touch on it a little bit, we had talked in our first discussion about the series that I did with Carson Hill, and the last episode that we did was when he released his Numa Macro, which is a something like whatever it's a Fallhaber motor, the same the manufacturer that a lot of the other pin manufacturers are using. But this one, I think I'll be making up the numbers, but it's capable of something like nearly twice the millinewton meters of torque as the standard. So what is that? So I can feel the difference. I own the machine and I run it I'm lining at like 5.2 volts, and I move my hand kind of slow anyways, and it's punchy. It gets in there. I feel it. It's meaty feeling. So is that just simply the number of like kind of wraps? And what fundamentally makes one motor more torquey than another? Is it the number of wraps of copper, or is it
Take a look here. So this is like a small SR series pancake motor from Fallhaber, 2607 series. So this is a data sheet, and basically in the data sheet we have every single spec about the motor. We see that we have things like the nominal voltage of the motor. This one's 6, this one's 12, this one's 24. So I can get this motor to run in 6, 12, or 24 volts. Of that, here's the efficiency of each of those columns, the terminal resistance, and you notice that's one thing that's going to change. A lot of these numbers are going to stay relatively the same between each motor. The terminal resistance is going to change because our nominal voltage is changing. So we have to have more resistance on these higher voltages to dissipate, so it doesn't act as much of a load. But ultimately, all these motors are still rated at 4 watts and 3.4 millinewton meters, even though one's a 6, one's a 12, and one's a 24.
Huh. Okay.
But the no load speed, we see the 6 volt 6600, 5900, and 6200. They all are arguably about the same no load speed. The torque constants, these are the engineering numbers that we go through and are very familiar with. There's the rated values for continuous operation. Rated torque, this was a 6, 12, and 24 volt. So 3.2, 3.1, and 3.4 millinewton meters. Rated current, rated speed, all exactly the same. These are your torque speed curves with continuous operation points, and a lot of what you're asking about what makes one different and the punchy feeling. The punchy feeling is going to come down to, it's not the reciprocation rate or how much, power the needle has behind it, because the motor is only going to deliver as much power as you demand from it, right? Let me pull back my full screen here. Whoops. So yeah, the motor can only pull as much power as you demand from it. If you hook up a 100-watt power supply into a 5-watt motor, the 5-watt motor is only going to be able to drive 5 watts. It's not going to draw the full 100-watt load. So the punchier, the higher motors is going to be potentially better depending on what the mechanism. This all comes down to the machine engineering and design and how efficient the mechanism is that's in there, because there's always going to be losses when you have bearings and other mechanisms put between the motor and the needle, which ultimately in tattooing, when you're doing work, when you talk about power is used to do work. So the work that you're doing when you're tattooing is obviously depositing the ink into the skin with a needle grouping of X size and some variables, simple variables like that. Ultimately, with a hand poke, you're delivering that power with your hand. Now the machine has to do that, plus account for any inefficiencies or losses. So like we saw, that Fallhaber motor had a 81% efficiency. So automatically we have to provide from our power supply little bit extra power to account for those losses. If we need 6 watts at the skin, then we need to increase, and that's not a number that I'm given that is accurate. These are numbers that there are no numbers for that, really. I mean, it's so arbitrary across, but there's no real number or standard of how much force a needle grouping takes to go into the skin. You know, how that scales across going from a single needle to going to larger groupings, you know, and the shape of those and how closely the needles are packed. So
yeah, and just the vast like array of skin types. You know, sorry, I'm sitting here chewing ice. I'm sure that sounds great. The vast array of skin types. You know, I just think about the amount of force that it takes to penetrate the skin of a roofer, you know, here in town who works outside all day, as opposed to, you know, a 20-year-old office worker who's, you know, has perfect skin and takes care of themselves. There are just too many variables, I guess, to get any kind of a meaningful range.
I wouldn't say there's too many variables. It's just that the scientific type research hasn't really been conducted yet. And I actually spoke to a gentleman from a university that's basing his PhD thesis.
You were telling me about this. I still haven't looked it up. Down in Texas somewhere?
Yep. So he's with Texas Tech and Idira. I'll have to look up his name here.
I wrote it down the last time that we mentioned it, but I haven't looked at it.
Actually, let's see here. Texas Tech tattoo. So he did this not too long ago. Tattoo therapy. He's looking at delivering drugs into the skin with you know, that's what his research, because obviously a university isn't going to fund I guess tattooing solely research, but research for tattooing tech opens research. But let's see, where's this? My lab. Lal, yeah, Idira Lal. Right.
There was someone. It's a female doctor in the Pacific Northwest somewhere in the last couple of years who was doing something similar, but with microspheres. Have you heard of it? Basically, they're encapsulated little balls of dye, and it's meant the same idea for tattooing, but it's for time released therapies for, say, diabetes or something like that, or something where if you may need to you know, some slow release, something that lasted for months on end, that they could be delivered this way. And I actually reached out but didn't hear back about the potential of. I was just talking in passing with someone, and they were talking about using these microspheres to encapsulate dyes rather than pigments. That would make tattoo removal much easier, because the microspheres could house dyes that otherwise your body would get rid of within a day or so. But because they're encapsulated in these microspheres, they stay, and your body can't attach to them or
then potentially break them with a smaller power laser instead of
a smaller laser could bust them open, and your tattoo would disappear.
Awesome. That's awesome. This is what inspired me to shoot my high-speed footage here, part of it. And not only that, I just wanted to have my own. You know how many people have a high-speed camera. I'm definitely going to bring it up. It's not brand new. I mean, you know, a new high-speed camera shooting the kind of speeds that we need in like 10,000 frames per second plus is going to be $20,000-$30,000 used. You know, so we were lucky enough to score one that shoots monochrome at a slightly reduced resolution. It's like a 800 by 600 native res at 1,000 frames per second, and then you can crop the frame at faster. So we've got a couple lenses and using it for now, because ultimately, it's tattooing research that's being done, and we're making some observations and things that I've actually talked to this gentleman at Texas Tech and communicated some of the things we've observed and shared our videos with him. So it's cool. We might have the opportunity to have some academic papers released on some of the things that we find. This is some of the footage that he put out. Let's see, we'll go full screen here. So depending on the art drawn, lines, shades, the tattoo needles are different.
I'm only getting the way that this Riverside is set up. I'm only getting a cropped screen, so I can't read all of it. I can see the needles moving though.
Oh, you're getting a crop screen? Let me see.
It's only because of the way that the...
Oh, because of the player, yeah.
Yeah,
I'm getting the same thing. Yep. So this is showing the different needle reciprocation rates. You know, this is, let me get the YouTube thing out. 24 hertz, 72 hertz, and I can't see the wrong because my camera's blocking it. How does the ink get in the skin? So this is a event that he captured, and basically what we're looking at here, the needle reciprocation rate was at 24 hertz. I believe my footage, my single poke, actually, I'm sorry, the line I calculated at like 50 hertz by the frames, and that's about what it was set at. But here's where we can see. Let me get through and scrub this. So the needle's coming down in, and one thing you'll notice is we're using gelatin. This isn't obviously human skin. Human skin isn't transparent, so you couldn't shoot through it and get this footage. So it's basically the same gelatin that you eat, and then we, I do. I think he was using the same things, and we'll pull up. He's using a gelatin hydrogel. So similar to what you were talking about those spheres, the gelatin hydrogel is gelatin that's encapsulated in a hydrogel. And the hydrogel is kind of to keep the gelatin moisturized, and it doesn't break down as fast. So it's kind of like it almost kind of simulates the epidermis dermis layer a little bit, but I don't think that it's, I skipped forward too much. All right, so we're coming down in, and that's one of the reasons why this is stretching so much, and why you're going to see that on my video and his video that ultimately, until the needle's getting down in this range, it's really not making a puncture. It's just stretching.
Just stretching, okay.
Yep. Let me play it here.
Yeah.
So he had access to a little bit nicer camera than I did.
Yeah.
And
that's
since
cool.
I've upgraded my lighting and done some other things, that's one big thing in high-speed photography is you get faster and faster, your shutter speeds get faster, the amount of light available gets lower, so you need a lot of light power to shoot at 10,000 frames per second and stuff.
What's amazing is how much perceived kind of needle penetration it took to generate like an eighth of the amount of ink in the cavity. You know what I mean? Like,
yep.
It's like if that was, if that was an inch, like just looking at that, so that's an inch from surface to tip of the needle, and then when that draws back out, you have maybe a 16th or an eighth of an inch of actual, ink sitting in the hole.
So then he's doing multiple punctures and recording how much the main effort of his paper that this video is around was how much volume of ink is pulled into the skin for each puncture. So he's trying to quantify and measure that. So you see we get more on the second puncture there.
Right.
But now we get this cool graphic that he did here that says schematically this looks like this. So basically we start with the ink puddle, the ink pierces. And this is similar to the video that you put out here 2 years ago, I think.
Yeah, with S8, yeah.
Yep. So as we go down, the needle is displacing the skin. It's not, how do I say it? The needle's displacing the skin. When it comes back up, the skin's not going to leave this big open area, right? So he's going to show that here. Is that, you see that it's closing up around the needle?
And this kind of illustrates part of what Sean Bellino was talking about in that video series that we did about the importance of an ellipse, the angle of penetration of the needle, as opposed to a round hole having an actual ellipse. So that's not perfectly, round, to force more ink or to I guess encourage a greater kind of vacuum into the skin.
Yep. And then this is some cool shots to it, some different angles showing the adhesion of the gel on the needle, which is similar to adhesion of skin on the needle. As you retract, the skin has a tendency to pull on the needle, just like that. So we've in the gel, and if you look at high-speed footage that's out there. I had some up on YouTube the other day of with the it's more cinematic type footage and scientific footage like this. But you can start to see that. But yeah, you can go on Google and Google Scholar and Google this gentleman's name and pull up his papers. He's got several. Idea allow, but cool dude.
Make sure to drop his
Super.
information.
One of the dudes is another dude that's not in the industry that's basing a good chunk of his life, several years of his life and time and everything in his university studies and finding a passion and studying this thing because it's when I spoke to him, he said it was an area that not a lot of people, let me get back to my camera, not a lot of people, there's not a lot of research being done in. So basically that excites him to want to make new discoveries in the room that it's not all figured out yet. Even in the academic world, there's nothing that's not black and white fact yet. So,
right. Examples like what you were doing
over here. Yeah, let's take a look at our video here real quick.
Yeah, but what I was going to say is these examples. Back within the, I don't know, I'd say within the last 5 or 6 years, you would hear people really pushing the idea that we should support tattooer-owned companies, and all of the slogans were for tattooers, by tattooers, and things like that. And I've always tried to make the point that we really don't want tattooers designing all of our tattoo equipment because it just takes too much work outside of tattooing. And if we're going to be good at what we do, we can't possibly be as good as we could be at at tattoo science and physics and fluid dynamics and electronics and engineering and all of those other types of things. It's too much work just to draw good pictures. So it's seeing something like this, like what this guy at Texas Tech is doing, I think is a good example of that, and what you're doing as well.
Yeah, so this is our video here that shows the event, and it's at a little bit different angle, but you can see. Basically,
and yours is the similar type of gelatin, same type of material.
Yeah, in the second video I'll show you here with the line entering. We did an experiment that he hasn't done yet. Every experiment that he's done has been a stationary needle going into the gelatin, which is basically what we're seeing right here. It's a single needle sitting still, just going into the gelatin. And this is, in this instance, the first time that it's punctured it. You can see on the left there's a previous experiment that the needle punctured. I don't just run one time. I turn the machine on and then I trigger the camera and then I go back through and I just grab the first 5 punctures of it. But here I'm only showing one. So what we're looking at right now, though, is that there's really no evidence of any ink in the skin right now. We start to see a little bit of a dark area, which is presumably the needle track. What we're seeing, it closing up what was left there. But then we start to see the ink flood back down in within the last several seconds there. So that's the last couple frames, and it just filled out right there. And then if we pull up the line video, so now we're translating the gelatin as we're hitting. So that looks more like the pop that he was getting. But what's cool that I noticed is that, damn YouTube, thanks. I'm going to get this open on QuickTime. So check out right now this. Pull it back to this when this just starts right here. All right, so see how the depth of this puncture that was just left compared to the rest of them? It's a little short. Watch what happens after this next puncture is made. Let me get the mouse out of the way. And
floods into both. Oh.
See it's thicker now?
Oh.
Now watch what happens to this one. I'll just play it. Just watch what happens to the previous puncture.
Okay.
Just take note of each. I'll rewind it and take note of each previous puncture. So we see this one. Not as noticeable, but now watch this one.
Mm-hmm. Yeah. Huh. So what's your theory on that? It's just that the ink is dissipating across the surface of the skin and further saturating that hole that was poked?
So here's my theory, is that right now we're stretching the skin and we can see that we have an interaction between the previous puncture and the needle. It's pulling that thing down massively.
Right.
But there's obviously ink there above the needle. You know, it's displacing as it's going down in. But when we come back up here and kind of get it to like a neutral to where the skin isn't really flexed anymore, you know, it's not sticking, but we just take a look at the depth of that guy and gauge it. It's still where it was when we started.
Right.
It's not until we come back up in here and now look, where is it? It's up inside of the area that's pulling up.
Yeah.
And it's not until that thing pops out in the same event that all of a sudden, look at that. It's like this, you know.
Yeah.
The other cool thing you could see on this video too is because the skin's moving. Check out when this thing comes off. The needle tip's right here, but watch where the well ends up. Because those skins stretched.
Huh. Yeah.
Yeah, so that's pretty cool showing that.
Yeah, that's really interesting. So your theory is, yeah, that's interesting because it doesn't, I mean, it looks almost as if, you know, you've hit on top of the same hole when it first starts to stretch, and then you see that that you're actually beside the hole, but it does really affect that previous mark, that previous hole. But then you're right, it completely disappears upon retraction. So does it just open that previous hole back up and flood ink into it? Hey, I do want to take a minute in this episode to thank today's sponsor, which is me, us, the Fireside Tattoo Network. Did you know that we have courses, memberships, and a lot of other free tools to help you become a better tattooer? Today, I'd like to spotlight our Fireside Foundations course. Fireside Foundations introduces the Fireside method of tattoo design, where basically over the years of working with painters and illustrators and other fine artists, I've adapted a specific kind of set of principles that I think relate the most to tattooing. And I've laid them out in an order of importance, from shapes to values to edges to colors, and we address tattoos, we build tattoos in that way. So this is kind of our beginner's course. It's perfect for people who either don't have an art background, maybe they're just starting to tattoo, maybe an apprentice or a 2 to 3 year tattooer, maybe even someone who's just trying to build a drawing portfolio to get an apprenticeship. This course is perfect for that particular artist at that point in their career. If you'd like to learn more, I'll drop a card in right here, and I'll also put a link in the video description so that you can learn a little more about Foundations. It's priced for apprentices and for young tattooers. It's very affordable. It's an entry-level product that I guarantee will change the way that you think about tattoo design. It'll help you to develop your own kind of unique mark making, which we talk about so much on this channel. So click one of the links, either the card or the link in the description below, to learn more about Fireside Foundations.
The question of, you know, things that I'm not an academic scientist. You know, I've got a lot of smarts, but how can we set up experiments and quantify and actually, you know, how do you measure how much ink was pulled in there before and then after that while you're tattooing a line at this frequency and moving? Because I'm doing things at to make them easier to film. I'm running at a little bit lower speed. So like this single line was actually lined slower than most people would line. You know, they're going to be running 80, 90 hertz, you know, speeds. I'm running down in the 50. I'm running like half that just because then it makes my frame rate, but I still get the velocity of the needle hitting. It's not like I'm running it super slow, which might affect some of the phenomena. So that's something else I got to test across a range of frequencies, which makes it tough to get the footage because then your frame rate scale with that. You need to shoot, you know, 1,000 frames per cycle, you know, have a scaling factor of your frequency to be able to get enough information there to see this. Otherwise, you just get one frame per. If you're running 120 hertz and you shoot 120 frames per second, I have one picture of every cycle of what I did. I don't have this information. So,
Right.
But yeah.
Oh, that's really interesting. That's awesome. That's awesome footage.
But yeah, if we can, I mean, it's a pretty simple process. I've got basically what I've got rigged up is like, I bought a whole bunch of microscope slides, and then I just have 3D printed some little holders, and I'll make the gelatin and pour, you know, into these things that I can shoot through and backlight. So the rig is, the camera is all in a Pelican case. It's pretty portable.
Okay. Yeah,
And,
I'm excited to test some of that out. I wonder. So you said that was you actually were pulling a line. So those individual punctures are a machine that are running across it. You're not making a puncture, moving and making a puncture. You're moving the way a tattoo machine would be, correct?
Let me switch back here real quick, and we can pull up on the post here. I think I have a picture of this guy.
Okay.
Which is basically just a little 3-axis cheap desktop CNC machine. Okay. And then I have it hooked up, and I think I was translating it in X-axis and filming from the front. And that machine was oriented. I've got several plugs that I print out here at different angles, in 5-degree increments. So that one was a 0 degree. The machine was standing straight up and down, just to try to keep everything in focus, because my focal plane at the f-stops I got to run, it's so shallow that the technicalities of capturing this, but yeah, that's basically how I'm doing it. And then I used this guy that I put up, which is the hand speed calculator. So I basically went out and said, how fast do I move the machine for how fast it's moving? If I want to get a certain spacing between there, and then boiled that down and ended up getting not bored, but just how can I make this semi more useful? So I popped this on the website that starts communicating that your hand speed is equal to the grouping width times the frequency of the machine times the advance ratio. So the frequency of the machine, if we adjust it, we see doesn't change anything with the needle grouping, how far it's spaced or anything. This is 3 punctures of 3 RL. So it's just changing how fast we need to move our hand. If we jack our machine speed up, we need to move our hand if we want to maintain these conditions. If our advance ratio goes up and we want a looser line, our hand speed also goes up. If we want a tighter line, it goes down. And this scales all as your needles scale, and it's really just a concept. If we switch on the show grouping width and increase the ratio here, we can see that, this has an approximate width of 0.75 millimeters. So in order to stack these at a 1-to-1 ratio, where they're right next to each other, that these are the parameters that you would need. That's how fast you're going to have to move your hand at 118. So I just program my machine to run this fast, and then it just does what I want it to do, because it's just math for me. But this is where I'm trying to communicate this to the tattoo artist. So obviously, this is cool to visualize and see how all this affects. And I mean, you can switch over to like standard needle. Let me turn the grouping count up. But a lot of it applies the same, and the grouping width isn't functional on this, but it's basically not a round circle around here, but your width of how far you're translating in that direction. But yeah, that's where that's going. We can show the calculator, but the app I think we'll keep until I got something. I'm not running into some technical problems with it. They're averaging timestamps and makes it hard to get a real accurate reading on your, we need 0.1 millimeter per second accuracy to be able to roll with this. So I struggle with that for a little bit, but one of the things I was working on as a tool,
Yeah, that's super cool. That was one thing that I was kind of wondering about with the hand speed calculator, is like what tattooers will comment on, I know, is will be asking, like, how
do I know?
How do I know? How is this useful to me? How do I want to, I don't want to change my hand speed, and it's and you shouldn't be really. You should make the marks that you mark. I'm not saying that you do
change your hand speed. I'm saying that if, let's say, I ask you to import a image into your line work into my app, and then I say go ahead and line it at a comfortable speed for you, and then I figure out what your averages are. There's variation between when you're doing shorter strokes versus longer strokes, how your speed tapers up and down, and what your profiles are. And I'm going to try to figure out what the best settings are for your machine speed to match those hand speeds. Or alternatively, if you want to fix, I want to run this machine speed and just change then you can train. But it's more, something to train the muscle memory, because that's ultimately what you're doing, either whether it's by feel, and what tools like this will do for guys like you were explaining earlier, just like I don't need numbers. I know what I'm doing. You know what I mean? But this now has all it's like when I was a machinist, this is the manual OG machinist, right? This is the guy that's like old grumpy. He hasn't washed his coffee cup in 3 months. And he's there saying, boy, I'll run this machine by feel and sound. And I'll make parts that are good and intolerance all day. And yes, sir, you will. You can. And the problem is that was what you learned 20 years ago. And you haven't adapted to the new technology, which is now a 5-axis CNC machining center, that you have to understand how to use the formulas that have been around for 100 years on calculating this stuff, but basic math to be able to say, okay, now I have to program this machine to do what I was doing. Now I can program 10 machines. Not saying that that's exact correlation, but the mentality of you're stuck in your ways and you're not, if having just by feel, but then you can put the numbers behind it, you can further have better understanding and knowledge to exploit, these things and say, man, I want to run my machine a little bit. I'll do my hand speed. Or, if you want to achieve certain effects, then you know exactly what you need to do with any machine to get that effect. It's not, guesswork anymore. It's not, right. Because a lot of, like, you get to whip shading. Like, you talk about whip shading, and it's like, that's such on a brushed machine where you have the bog, you have not only how fast you're accelerating your hand, but how fast the machine's decelerating, and that's playing into how far your spacing is. And all these are changing instantaneous. So it's just comes back to the consistency and reproducing exactly what you want, because getting it in the first time is important. Yeah. Not having to go back and reline or, pack in the same spot and that's sitting in tattoos. I've been tattooed by multiple artists, and some not as good as others. And I felt the bitter ends of that. And, man, the last guy didn't go over the color 4 times. How come this is hurting so goddamn much? You know what I mean? So, right. Solving that not only for the artist, because when I hear that, somebody has bought my product and then used it for a while, switched back to what they were using or tried something new, and then ended up having to go back to it because they found that they were saving, X% on their tattoos as far as the time it was taking them. And it was easier. And, at the end of the day, that's the questions I've been asking to people like that. I'll point back to the confidence in the machine's going to do exactly what they know it's going to do every single time they hit the skin. So it's just boom, 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 and just work and just get it done. And, that's it. So,
yeah. Well, that was the one of the great reasons for this big resurgence of our explosion of rotary machines is that the machine does operate basically, if you keep it oiled, the mechanism oiled or whatever, it does run the same way every time. And that was something that people like me that came up in the coil eras that I tattooed based on how my machine was behaving that day, and if I didn't want to take the risk of trying to play around with the contact screw and completely throw it out of whack, then I just learned to it's not, I'm just gonna have to bump it up a little bit and deal with the heat and wrap a paper towel around my hand because it's getting super hot today, and it's spitting ink, or I'm having wild fluctuations, and that was the main thing that along with the weight that kind of pushed people away from coils and into rotaries in the first place is just consistency. So if you can further that consistency with a power supply or with new technologies, where I know this rotary does the same thing every time I turn it on, and if it's not getting ink in this person's skin the way that it did the person's skin yesterday, then now I have this other set of tools that might help me determine what steps to take next to make sure that I can get through this thicker skin or softer skin or whatever it is.
Yep, just like any problem, you need to identify your variables and areas that you have control over first. In this formula that I'm presenting, you have control over certain things that are inputs to the variable, like the grouping width. That's just going to be a factor of what grouping you need to use to get the job done. So that's not really something you could select a different grouping, but at the end of the day, or choose a different needle size. But at the end of the day, that's outside of your control. And once you select it, it's a fixed. It's not changing as long as you're using that grouping. The needle's not getting smaller. The spacing isn't changing. That's a fixed now that you've selected it. Mm-hmm. So that's just like if we look at the other variable on the hand speed, it's a frequency. So now if you can fix that frequency, now the only variable left is your hand speed. So at any capacity, if your machine frequency is varying, and you can see, let me just check here to confirm what I'm thinking. So we got 88 to 89, and yeah, it's about 1 millimeter per second difference for 1 hertz with this grouping here. So it's not negligible, I guess. You know what I mean? It's something that. Sorry, trying to pop my window back open here. That's all right. So yeah, it's something that you also got to think about with brushless machine or anything else, the source of the power that you have coming into it, because a lot of the coil guys back in the day, even with their machines, and with the coil, you're talking about like a tuned system. You know, it's you have a lot of variables on that come down to, I've heard one of the guys I was helping build some coils for, I traded out some tattoo work for, you know, one of the shops I was working at had a really nice laser, and I had access to a lot of material and other things at good cost, and he had known I did work, you know, machinist and all that, so he hit me up about taking some side plates that he had off 1/4-inch grid and just making CAD files. And I asked him about cutting them, and he's like, "Oh yeah, can you cut them?" It's like, "Yep. How many you need?" So
that's cool.
But when we talked about geometry and got into some of the, you know, it just has to be that way. I'm just scratching my head and saying why, you know. But with a coil, like if you notice, like if you change the mass of the grip on that, if you change how when you hold it, it changes how the machine is actually, if you listen to it carefully and if you actually look at the frequency that it's running, doing things like that are changing it, because you're changing the mass of the frame that everything else is attached to. And depending on its rigidity and several other properties of it, that's going to change how it's responding in the tuning of the system. Small little things like that. And like you're explaining, the contact screw, all these little variables that you're fighting on a daily basis instead of getting in and doing your job. And because like that's one thing where machining has heritage and history and other things behind it that, you know, guys that usually come into the machining trade, it's not because you're going to become a millionaire. You know what I mean? Some guys have aspirations, but it's because you want to make cool shit. And you know what I mean? You want to have some skills and do something that not a lot of people do. You know what I mean? At the end of the day, because it's a dying breed. It's something that there's not a lot of in the U.S. left anymore. So, you know, when I was 18, I bought a 1939 Bridgeport, and I still own it to this day. It was actually the 131st one ever made pre-war. Wow. So it's actually a piece of history, and that's like, you know, I don't want to destroy anything like that, but at the end of the day, there's time for efficiency, and if you want to take a ritualistic time to set your coil machines up and do a piece, you can still use them. You know, you can you can still for sure do all that, but at the end of the day, yeah, if you're looking to run a business and make money and improve your efficiencies and, you know, do things like that, then having tools that require the least amount of maintenance and, you know, things like that, which is the rotary machine like you're describing. You just put a little bit of oil on it and the thing's going to run as long as the brushes are good, and as long as, you know, in the brushless case, the motor controller is not burned out, or, you know, bearings are still good. So
yeah, and it'll, you know, I don't see coils ever going away. First off, they they last forever. You know, you change springs. There's almost every part that can break is easily, you know, interchangeable, as opposed to, you know, if a rotary of mine breaks, I'm just going to go buy another one and toss that one. And I have noticed I do a good number of shows, and I felt like, I would say over the last 4 or 5 years leading up to the pandemic, when there were no shows, it had gotten to a point where I almost never heard coil machines at a show anymore. Yep. It was pretty quiet. You could hear the main stage, hear the music, hear people talk. But this year is the first year back. There are a lot of people at tattoo shows using coils. So I wonder if people didn't like use that time to like dive back in, rebuild their old coils, or just get introduced to coils for the first time if they never had been before. So I feel like we'll see a big kind of pushback of coil machines. Plus, they look so much cooler.
That's the characteristic of things. Is definitely the buying a machine. People ask me a lot, what machine should I buy? What machine should I buy? And To a degree, I don't want to discredit what machines can do, because I know that, with the right technology, that machines can do more than just make needle go up and down. But for the most part, that's at the end of the day what most artists boil it down to, is machine make needle go up and down. But
Right.
then when you flip the script on them and you say artists make ink go in skin, and they say, but there's a lot more to our jobs than that. And you say, well, there's a lot more to your tattoo machine's job than just making the needle go up and down. It's got to do that and hold a steady speed, just like we're saying now. So any varying frictional load in the cam system or the design, that's the stroke length is going to affect, things like what we're talking about with how hard it's hitting. It comes down to the amount of velocity that the needle has, which has, playing into how much speed. You run it faster, the needle's moving faster. But also if you were to move the needle at the same speed and take one needle bar that weighed a very light amount and one that was a little bit heavier, the other one has more inertia and more mass behind it, and that's going to perceive as a harder hit, so
Yeah. Something that might be fun to talk about when we do this in person as well is another variable in rotary machines that I've noticed being pretty significant from manufacturer to manufacturer are cartridges themselves, and the stiffness or lack thereof from one manufacturer to the next. So, for example, there are several cartridges. If you push a plunger on a cartridge, some of them will you barely have to touch them and they fly out. Others really push back on you. And I noticed when I started using this latest machine of Carson's that the cartridges that I was using from one manufacturer started spitting all of the ink out as soon as I got out of the ink cap. I would dip, and as soon as I pulled out of the ink cap, it just emptied the ink. And I thought for the first little while, I was like, maybe I'm just getting bad.
You're attributing that to the membrane stiffness?
I think so. I think that that's a punchy machine, and I was using one of Carson's cams that has a very severe slope. So it was like it's in quickly and it's out quickly. So I feel like there's just enough chatter in that cartridge that the needles just spit the ink out. They just weren't writing smoothly in the cartridge themselves. So I wonder, because I've changed manufacturers and I'm not having that trouble anymore.
One thing that's interesting about the cartridge membranes, it's caused a lot of problems in the industry with the rotary machines, because the rotary machines originally were driving needle bars. There was no, you had a rubber band on it or something like that, and the manufacturer would usually put a little return spring in there to make sure that the needle was retracted when the machine stopped, that it always retracted on the upstroke. Now you got the cartridges, and it's throwing in, you see things like the jump start on power supplies and having to overcome that cartridge resistance. But what's interesting about it is, once the machine's running, it's a negligible factor on the amount of power that it takes to run the machine, because the biggest impact is when you start the machine, you have to push that membrane down the first time, but then once it's pushed down, it pushes back up on the motor. Just like we talked about earlier, that motor is acting like a generator, which then on that is putting energy back in. So then it does take some energy, but it actually comes down to like the frictional losses of the rubber, and because the rubber is actually heating a little bit as it's stretching, so you're actually putting energy into that it's going to take. But for the most part, if you watch the current draw with or without a cartridge, it's a negligible increase when you look at it on the machine. It's pretty cool. It's like the physics and science of like things that just dig into this, and this being my full-time job of like, I get paid to sit here and learn about this and dig and just, figure this stuff out. And not only that, through solving problems, helping other people out, seeing what the cause of trying to build better machines and reduce failures, and, looking into all those. So that's,
yeah, and discover new problems.
But one thing I'm thinking with what you're saying, I'm gonna.
I wonder if we couldn't. I know the manufacturer that I was using, and I actually still have some of those cartridges. I wonder if when you're here in town, if we couldn't put the high-speed camera on the cartridge and see if we're getting a lot of chatter in the like up and down motion, as opposed to an oscillating motion from the needles in the cartridge. All right, back.
Yeah, I think so. Give me 2 seconds. I gotta use the restroom.
Well, I was gonna say we're over an hour
good?
in. I think we're probably good for an intro. Do you want to? So one thing that I wanted to to say one reason that we're
here. We could finish
that
that
we did
topic
this kind
up
of.
here. I was going to show you this.
Well, if there's something else you want to show me, go ahead. We can pick it back up if you want to take a bathroom break.
Okay, yeah, it was some high speed of cartridge, and there's actually air draft caused down there that I'm wondering isn't some of the sputtering that you're seeing. I've got some high speed that I captured of a cartridge starting with some dried ink in it, and you can see the flakes getting pulled back up by these air currents. It's pretty cool.
Yeah, well, let's check that out. Sure.
Right,
okay, go ahead.
Sorry about the technical difficulties. This is still new to me. I just set it up, and I've been trying the last couple of days to get familiar with it just for this event, and continuing to put stuff like this out because.
No problem at all. Yeah, I'd love to see.
All right. These are all experiments. I got this software that does or this app that does tracking, point tracking and videos. So I was playing with that. I'm sending the wrong. There we go. All right. Pop this up.
There
we go.
Okay, now I see.
All right. So you see the little chunks falling out of it, and you see like up here how some of them get drafted up every once in a while without touching the needle.
Right. Isn't that interesting?
So like this guy right here. And let me scrub through it and find a floater.
So that's just the needle retracting, probably with
the needle. Here's a good one. What's that?
I guess it's the needle retracting along with all of the dried particles are kind of creating a wind kind of gust, a vacuum that's pulling those little particles back up into the cartridge.
So the diaphragm is presumably acting as a pump. There's going to be some interaction with the air and the needle. Not much, but if you ever heard of Schlieren imaging, I've actually been working on a setup to try to measure this, but it's such a small amount of air that I need a real sensitive setup, and we're going to get the mirrors. And
what's the term again?
Schlieren, yeah. So I've got I did a basic setup and tried to capture it on that, but it was not sensitive enough, like I said. So I've got to get it requires a spherical parabolic mirror, and yeah, we won't pull that up, but basically you can see the differences in air densities, so you'd be able to see the air currents on here.
Interesting. Okay.
But yeah, if you watch these guys coming out right here as we go through the frames, like that guy is now like pretty much weightless and now coming back up. But if we track it, and it's from when it was falling right there, we could see it's still falling, and then we see a gap here. It's no longer touching, so it's not like rubbing. But all of a sudden it's moving back up. And I think on some of them you can almost see two interactions on the smaller ones.
Huh.
Yeah. Like that guy right there. Like, watch that guy.
Yeah.
Like it comes down. Yeah. So it came down. It's kind of behind the needle, I guess, right there. But it comes into frame right there. And then it comes up. And then we come down. And then it comes up again. But that was something that was completely by accident. Like, I literally was just had a cartridge and had taken a 15-minute break and came back and, went to start the machine up, or accidentally started the machine up, and the camera was, just happened to have it in the buffer of the camera, and looked at it. I was like, man, that's kind of cool. Let me save that.
That's really interesting. And I would love to have that exact type of footage with the cartridges that I'm talking about, with the cam setup that I was talking about that just literally spits all of the ink out. You'll have that happen. I've had that happen a ton of times over the years with a specific needle. I mean, not just cartridges, needles on a bar, back when we were making our own needles, 20 years ago, where you would have maybe just a little clump of solder where the needle grouping was on the bar, and it would just like, as the needle grouping went forward, the little clump of solder just splashed all the ink out at once, So that stuff does happen. But
or like you're saying, how it is, the consistency of how it's riding in the tip, and
exactly.
if it's
so there's a reservoir. Yeah,
that's
so
why
the
I like
reservoir is holding
bending
the
and
ink.
doing stuff like that helps, because it helps keep where it's riding in the tube at the same time
Exactly.
and not doing stuff like this. Yeah.
Yeah. But with these cartridges, the problem I was having was not specific to a cartridge. It was specific to a cartridge brand and just the liners, not the shaders. So that was kind of interesting too. So I would love to have that exact footage when you come to town. I'd love to play around with
We're
that.
going to play around with it. I mean, the biggest pain with it is that it's like, to save, it's because it's a little bit older. You know, you're talking like, you know, save a clip out is like 20 minutes, 30 minutes. So
that's cool.
but you know, shooting it and getting that, if you're not looking for something that you're trying to capture every frame and you're cool, just get like a cell phone video off the display or like an external capture or something like that. But I'm still playing with that too. It's my time is just, I'm bouncing around every day, just trying to handle so many things. And that was my birthday present to myself this year, was the high speed camera. So I saw it available and it was within my budget range. So our budget range here. So I said, hell yeah, let's get it.
Oh yeah, excuse me. I can't wait to check it out. Well, one reason we were doing this, what was supposed to be a teaser episode, but now it's like a full-on episode, it was so that we could ask folks who are watching the show. Our goal is to get together in person and run some of these tests and experiments. And what we'd like to know is if there are any specific questions, ideas, you know, suggestions that anyone has to help guide us so that we don't just turn into complete mad scientists and, you know, go crazy. So you can either email, I guess you can email either of us or both of us would be great. Maybe that would start a conversation. Jake at Fireside Tattoo, or
A. Williams at tattcom.us.
A. Williams at tattcom.us. So I'll drop both of those emails in the show notes, or you could just comment if you don't want to take the time to send a message. You could just comment on this actual video. We'll make sure to look at these comments before we set up and start to make our plan. We don't have a time frame just yet, but I hope we can do it soon, shortly after the holidays.
Yeah.
It's, right now it's early December, so we have Christmas and all that coming up. But
and then we'll have, like we obviously said, the high-speed cameras, but we had mentioned, you know, bringing out some electrical test equipment and, you know, boiling down, you know, maybe some electrical theory, and we can dive as deep as people want. Obviously, it would be very helpful to have any input from viewers, because like you said, otherwise we might just get into it, all the tangents that we find fun, and everybody else like, oh man, we wish you would have done this. So let us know for sure.
Yeah, exactly. Well, cool. We can wrap it there. I appreciate it, everybody, and make sure to leave us a comment. Let us know. Thanks, Aaron. Appreciate it.
Hey, thanks again for taking the time to hang out with us and get to know Aaron a little bit. That was a pretty fun episode. I hope you will agree. Like I said before, make sure to sign up to our mailing list if you have not already, so you can keep up with what we're doing, what's happening in the world of Fireside. Also, if you haven't yet been to the new firesidetattoo.com, a lot of our content is being kind of repurposed over there. If you just go to firesidetattoo.com and click on tattoo topics, all of the content that we've produced over the last decade is slowly being added under keyword categories. So if you want to learn specifically about tattoo technology, or about tattoo science, or about techniques, physical techniques of putting ink in skin, you can kind of sort through all of our years and years of content by those keyword categories, and we're slowly adding new content all the time, or grabbing those old episodes and dropping them in the appropriate categories. So make sure to come back often, because it's always, that library is always growing. Thank you guys as always for supporting what we do. We'll catch you next time.